For today's class, we're going to cover Chapter 28, Sections 6-8, with these concept questions and these exercises. So starting with concept question 11, go take a look at it, and then come back here for guidance. I'm going to draw this picture up. You have a battery that's connected to a resistor and a light bulb, and then in parallel with another resistor and another light bulb. And these resistors, same resistance, and these light bulbs are identical. Okay. This battery has some voltage, and we're indicated 2 points, 1 and 2. Okay. So this bulb can be unscrewed, which means if it's unscrewed, there is no connection between points 1 and 2. Okay. So you just take the bulb out of the circuit, it breaks the circuit. So if that happens, what happens to the brightness of, the potential difference across 1 and 2? So what happens to delta V 1, 2? Does it stay the same? Does it get bigger? Does it get smaller? What happens? How can we determine that? Okay, so first off, when the bulb is in the socket, okay, that means current can flow because the battery can push current through this resistor and through that light bulb, and it's glowing. Okay, so there is current flowing, so we can indicate a direction of current there. And then that means if current is flowing through the light bulb, it is also flowing through this resistor. So is there a potential drop across that resistor? There is. When the light bulb is in the socket, current's flowing, and therefore there's a potential difference of delta V equals IR by Ohm's law. So if the potential difference between here and here are delta VB, then the potential difference between here and here will be delta VB minus IR, because that's the potential drop from here to here. Okay. So if this is the potential difference when the light bulb is in the socket, and then you pull the socket out, which kills the current, what happens to the potential between points 1 and 2? It gets bigger, because then this goes to 0, and we have that 1 and 2 have the same potential, have the potential difference as same as the battery. This resistor basically is not doing anything. Since no current's flowing through it, it doesn't change the potential at all. The only time you get a change of potential is if current is flowing. Okay, very good. Now let's look at 12. This introduces grounding. These are two light bulbs, A and B. And here's a battery with some potential across it. So the question is, these two bulbs are right now, they're glowing, they're equally bright, and they're glowing. What happens when you connect this switch, flip this switch? So it's connected to ground. That's a symbol for ground. What does grounding do to a circuit? Okay, so grounding establishes a 0. That's really all it does. It establishes a 0. There's some other complicated things that could happen, but in general cases, all it does is establish a 0 potential. So I know that at this point, V is 0. And since I know V is 0, I can say things about what the potential is here and what the potential is here. Not just delta V's, but I can actually say what the potential is at a point. So grounding, all grounding does is just establish a 0, which then allows us to find potentials at other points, not just relying on potential differences. So if that's all it does, then what happens to these bulbs? They still glow with the same brightness because current's still flowing through here, through this bulb and back. This is still a circuit. All this does is establish that that point there is going to be 0 volts, which then I could figure out the current flowing through these and find out what the potential is here, and it would be equal but opposite up here, and the difference between here and here would be equal to the battery. Just remember what grounding does. It just establishes zeros. Okay, number 13. We have these three curves, and this is the potential difference across the capacitor versus time. Okay. What we're told is we discharge a capacitor 3 separate times. We discharge it across 3 resistors. Okay. And the resistance associated with this potential versus time curve is R1. For this one is R2. For this one is R3. The question is, rank these 3 resistances. So we have to ask, well, how is resistance related to this potential difference capacitive voltage across the capacitor as a function of time? How are they related? Okay, well, we have a relationship that says Q equals Q0 e to the negative t over tau, but tau is RC. So R is related to the charge on the capacitor, and the charging on the capacitor is related to C delta V of the capacitor. Okay, so if R is big, then this exponent is small, okay? And that means that the change, as time ticks on, the change gets smaller. This RC we call a time constant. We use time. And it basically describes how fast will this change. Okay? So if this is really big, then when t starts from 0, it takes a long time for it to reach RC, or to reach tau, which means it doesn't decay very fast because this stays a small fraction. Okay? And so the bigger R means the bigger tau, and the bigger tau means the more gentle the curve. So R1 is actually a really small tau. Okay? It's a really small resistance because it's changing really fast. Okay? That means T gets bigger than tau very quickly. But R2 is changing the slowest, which means R2 must be the biggest because it's changing only slowly. And then R3 is in the middle. So we have R2 is greater than R3, which is greater than R1. So again, tau is a rate, as a value to describe how fast it's changing. So if it doesn't change very fast like this one, that means tau is big. It takes a long time for it to change significantly. So R2, which is proportional to tau, is big. All right, let's move on to our exercises. 27. Okay, this is practice with resistors in parallel and series. So we have identical resistors in this fairly complicated setup. Those are all identical resistors. We'll just say they each have a value of R. And the question is, what is the equivalent resistance between points A and B? Here to here. Okay, well, we know that in series, the resistance is add. So R equivalent will be equal to this resistance we'll call R middle, which is all of this, plus this resistance, which we'll call R right. It's on the right. This is just R because it's only one resistor of resistance R. And so our question is, well, how do we find the resistance, the equivalent resistance of this middle piece and then this one? Well, they're in parallel. So how do we find parallel resistance? Let's say R middle is equal to 1 over R plus 1 over R, and then all of that inverted. Since they're identical resistors, it's just 1 over R plus 1 over R. Which that gives us 2 over R inverted, so equals R halves. And that should make sense. It should be less than R, because if each of these are R, then in parallel it should be smaller resistance. There's more path for the electrons to travel. All the electrons that went through here could now go through here or here, so they can move more easily through this piece. Okay, the same can be said over here, and we'd get R right equals R thirds. So it's even smaller of a resistance. Okay. All right, now with that, we just add them all together. So we get R plus R over 2 plus R over 3. And R is 100 ohms. So when you plug that all in, you end up with 183 ohms. And we could check that and say, does that make sense? So if each of these resistors is 100 ohms, well, we know that the total resistance ought to be bigger because 100 is in series with two others, so it must be bigger. Now, it's not going to be bigger, it's not going to be 300 ohms, it's got to be less than 300 ohms because in parallel, this is smaller than 100, and this has to be smaller than 100. And so well, we know it's got to be between 100 and 300, and it's 183 because these ones are much smaller. This one's smaller. Okay. All right, now 29. Okay, this is a circuit with 3 resistors. Okay. We have a 10 ohm resistor, a 5 ohm resistor, and a 20 ohm resistor. We have current flowing in from the right. And we're told that I'm going to call this P1 is 40 watts. So I'm going to call this resistor 1, this one 2, and this one 3. Okay, we're told that this resistor is dissipating 40 watts of power. Okay, 40 joules of energy per second. And then the question is, well, what is the power dissipated by these ones? Okay, so let's just focus on 5. Well, how would we find the power dissipated by the 5? Well, power, P2, that's going to be equal to IV, so it'd be the current flowing through 2 times the potential across 2. Since I'm given the resistance, it probably means I need to rewrite this to include resistance, which could be written as I2 squared times R2, I squared R. All right, I could have maybe written it as delta V squared over R. The reason why I want to choose this one is because if I know this one, I might be able to find the current flowing through this one. And if I do, what does that mean about the current flowing through this one? It is the same, because these are in series, so the current flowing through one must go through the other. So if I can find the current through this one, and I can find the current through the other one, and then I can find its power. So to do so, let's pause on this relationship, and let's find the current flowing through this one. So P1 is equal to I1 squared R1. Therefore, I1 squared, which I'll leave it as squared since I'm going to need it as squared anyway. I1 squared is just simply P1 divided by R1, which is 40 divided by 10, which is 4. Okay, so it's 4 amps squared. Okay. Now having that, I can plug it in there, which then 4, because this is squared again, so, and they are equal. I1 equals I2 since it's in series. Then I can find that one by just saying it's 4 times 5, which equals 20 watts. So this resistor is dissipating 20 watts. And we found it by first defining power and recognizing these have the same current. So we found the current from our knowledge of the power on this one and its resistance. Okay, now the last one is find the power across this one. So we ask ourselves, well, I could write a P3 equals I3 delta V3. But how is the currents related to it? I know the resistance, maybe I can write it this way. So I know it's resistance. But the thing that's the same between these ones is the voltage. These are in parallel, so the voltage is the same between this leg of the circuit and this leg of the circuit. So I might want to say P3 is delta V3 squared over R3. Use that form of power. Because if I can find the potential across this one, which I can, that's the same as this one, and I just divide by its resistance. So let's pause. Let's find delta V3, or delta V1, 2, the potential across 1 and 2. Well, that's going to be equal to I'm going to just call it 1, 2, which is the same. And then it's going to be through both of those. And so it's just going to be R1 plus R2. Okay. And so that's the potential across the top leg because they're in series, so the resistances add. And so with that, I can calculate delta V12. I get 30 volts. Plugging that then into here, I get 30 volts squared divided by 20 gives me 45 watts. So I like this problem a lot because it has some good review pieces in it. We had to review power in its different forms using Ohm's law. So there's a review of Ohm's law. We had to review resistors in series. And we had to review resistors in parallel to be able to answer these questions. Very good problem. Okay, our last one, 35. Okay. And what we're told is we have a capacitor that has a certain charge on it. I'm going to call it Q naught. And we hook it across a resistor that has a resistance R. And this capacitor has a certain capacitance. So we know all three of those numbers. Okay, we know the resistance is 1 kilo ohm. We know the capacitance is 20 microfarads. And the charge, the initial charge, is 20 microcoulombs. Okay. Now our question is, how much time elapses from the moment we connect those to the time that the charge on the capacitor is reduced to half its original value, or 10 microcoulombs? How do we find that out? Well, the relationship we know is that the charge on the capacitor at some time is equal to the initial charge times e to the negative t over tau, but tau is RC. Okay? And so if this is the time we're looking for when this is 10 nanocoulombs, or microcoulombs, when it started with 20 microcoulombs. So we basically need to solve this for t. We know everything else. Okay, so solving for t kind of is reversing the derivation that we used to get this equation. So let's divide the Q0 over and then take the natural log of both sides. Okay, so I divided Q0 over and take the natural log, which means I have to take the natural log of this. But natural log of e to something is just the something. So that's negative t over RC. Now solving for time, we get time equals a negative RC natural log of Q over Q0. Okay, very good. So now we just plug in our numbers. We plug into the 1,000 coulomb. We make sure we have these in SI units. And so this is 1 times 10 to the 3 ohms. This is 20 times 10 to the 6 farads. These don't matter because they're the same unit, and so they're going to cancel out. The units will cancel out. And it's just a ratio. If you plug in all your numbers, you'll end up with 14 milliseconds, which is 0.014 seconds. And that's a reasonable value. Charging a capacitor is generally very quick. It can be very quick. Depending on the resistance, a kilo ohm resistor is not that big. And if you did a mega ohm, it's more noticeable time. You can get the time for capacitors to charge or discharge to be in the minutes, but it requires large resistances, making the time constant very big. Thus, it takes a long time to change.